So here's our first couple of examples dealing with the concept of a basis of a vector space. So first of all, I have the definition up here in the corner. A basis for a vector space V is a collection of vectors in V that meets two criteria. The collection of vectors needs to be linearly independent, and it must span V. And the idea here is to find a generating set for V. So a collection of vectors where we can form any vector in the vector space V as a linear combination of these like building block vectors that are in our basis. The linearly independent requirement tells us that we're going to make this collection of vectors as small as possible. We're going to get rid of anything that's just a linear combination of the other vectors in the set and get this down to just the essential elements. And that's one way to think about basis, is it's a collection of building block vectors that are, each vector in this set is essential. There's no redundancies. So example 2 asked, is this collection of 4 vectors, notice that these are vectors in R3, is this collection of 4 vectors a basis for R3? And I didn't leave a lot of space here because we can answer this pretty quickly. The answer is no, because if we have 4 vectors in R3, there's no way that they're linearly independent. If you think about the way that we determine linear independence for a set like this, we would create a matrix whose columns are these vectors. If you get a pivot in every column, that would tell you that it's a linearly independent set. Well, if there are 3 rows to that matrix and 4 columns, there's no way you're gonna run out of rows before you can get a pivot in every column. So we can say no, this is not a basis because it's not linearly independent. We don't need to say anything about span. I don't care at this point if this collection of vectors spans R3. If it does or doesn't, it doesn't matter because it's not a linearly independent set, so it can't be a basis. And we just move on. All right, so here's example 3. Now we have only 3 vectors in R3, so we can't immediately say dismiss it the way we did with example 2. 3 vectors in R3 were asked if this is a basis for R3. So now we need to actually check these 2 criteria. Both of those criteria can be checked by setting up a matrix whose columns are these given vectors, and then reduce this to at least to echelon form. And all you really need is echelon form. So to do some quick row reduction on this, let's say I want to first get rid of the -3 in this position here. So I'm going to do 3 times row 1, add that to row 3, make that my new row 3. So I'll have 3 plus -3. 3 times this will be 9 plus -3. And then 3 times this would be -12 plus 9. And now I'd want to get rid of the 6 right here. So I would do -6 row 2 plus row 3. Make that the new row 3. So I'm going to copy the first 2 rows the way they are. And now I can do 0 plus 0, -6 plus 6, -6 times this. So that'd be +6 plus -3. Okay, and we've now got this thing in echelon form. Here are the pivots. So the fact that there is a pivot in every column tells me that the vectors are linearly independent. So I'm just going to put linearly independent, check, because there's a pivot in every column. Remember how that ties into the definition of linear independence. If we were solving the homogeneous system where we have C1 times vector 1 plus C2 times vector 2 plus C3 times vector 3 equals the 0 vector. So if this were augmented with the 0 vector here, then we would end up with C3 equals 0, so C3 is 0. And then when you do back substitution, you end up with C1 equals 0, C2 equals 0, so it's linearly independent. Just as a reminder of why pivot in every column tells us that. Does the collection of vectors span V? Well, so now, instead of the definition of linear independence, where we're solving where this equation, or this linear combination of the vectors is equal to the 0 vector, now think of it as we're trying to generate just any vector B in R3. So you have this augmented now with B1, B2, B3. And again, you do the row reduction. Once you get over here, you're going to have some combination of B1, B2, B3 in your constant column over here. But the important thing is there's no way you're going to end up with a pivot in the constant column. There's no way you're going to end up with an inconsistent system if you have a pivot in every row. So we know that this collection of vectors spans R3 because there's a pivot in every row. So because there's a pivot in every row and a pivot in every column, we know that this collection satisfies both requirements, and so the answer here is yes, this is a basis for R3. And just one more point I want to make in this video. So notice, I said previously in the notes that the standard basis for R3 is 1, 0, 0, just the unit vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. That collection of vectors is linearly independent. Picture a matrix with these guys as the columns. You have a pivot in every column. You have a pivot in every row. It does span R3. This is what we call the standard basis for R3. But this is also a basis for R3. So just I want to stress that the basis for a vector space is not unique. You can come up with different bases for a given vector space, as you can see here.